So I just wrote down what we started with yesterday, namely what the setting is now. So we switched to not necessarily commutative rings now. And so we're looking at Ivanara-Gorenstein rings. And so far we haven't really said anything about the graded case, but the important part is that in the graded case, you consider your Gorenstein ring, Ivanara-Gorenstein ring, positively graded, and the degree 0 part is the field. And then you can also define this Gorenstein parameter, which is defined in this formula. And then also we decided what we would consider as maximal Cohen-Macaulay modules. So these are all the modules that have for x, higher x against the ring vanishing. Okay, so so now today, just one example, so that this is in the commutative case, this actually is precisely what we're looking at. So for example, we could take SA to be as before, so S is always the polynomial ring or regular local ring, and then modular or polynomial. So this is indeed a complete intersection ring, and that would be, for example, a commutative Gorenstein. So particular everything holds for the setting before that we had for the matrix factorization. Okay, and so now let's introduce the singularity category. This was originally defined by Buchwald, but not under this name, and the name is was first used, I think, by Orlov in his paper in 2004, which is the first paper on the singularity categories. It's called Triangulated Categories of Singularities and Drawings in Landau-Ginzburg model. And I think Buchwald called this just the stable derived category of A. So what is the singularity category? So we take our Ivanara-Gorenstein ring, and then we define the SG of A to be the derived category of over A modulo perfect complexes. So this singularity. And so this has degree mod A has a triangulated structure. So this is in particular, this is the triangulated singularity category. So why is this called singularity category? Because, well, it should tell us something about the singularities of A. And so you can, for example, see if A is regular. So we haven't really said what regular is for a non-commutative ring, but as an example, if regular, then CB A is just 0, because then this is just the same as the perfect complex. And so, okay, I have to leave out a lot of things because I want to really state the theorem and also do an application or an example. So this is the category, and now the theorem. It's the non-graded version. So if we have A, B, and Ivanara-Gorenstein, then we have equivalence categories. So write it a bit in a funny way. So we have the maximal Cohen-Macaulay modules under A. We have to take the stable version. And then we have singularity category of A, and this is an equivalence which is given, which is this is the inclusion factor. So this is here, and also this is they're also triangulated, so triangulated equivalence. And so this is the result, but then actually in order to prove this equivalence, Buchholz introduces a third category, which he notes, I think not in this manuscript, but then later on as CR of A. So these are the what's called complete resolutions over A. So this is so these are basically unbounded acyclic complexes of A modules, or finitely generated projective A modules, such that also if you take the dual of that complex, it has the same property. And so somehow, yeah, you can. In my notes, I actually defined this properly and also how to construct it and how to get from such unbounded complex back to the maximal Cohen-Macaulay modules and to the singularity category. But what's then really proven is that you get an equivalence here given by the Syzygy functor, and you get an equivalence here given by just truncating this perfect complex, and then gives the equivalence here. So this is the theorem, and so we have, and so if we are in our previous context with the matrix factorizations, we see that this MCM R, this is just the category of matrix factorization. So it's precisely this singularity category that should measure the singularities of A. And so now, from a more geometric point of view, Orlov considered the graded version of this. So this is, oops, it's not 4, I think it's, this was 1. I left out some stuff. So this is now 2. So Orlov's theorem. Which is now the graded version. That gives also some more structure of these categories. So now we are in this graded case. So we have again Ivanara-Gorenstein ring graded, and we have this Gorenstein parameter, and somehow this Gorenstein parameter will tell us how the category of coherent sheaves over proj A behaves. Namely, here, so here, Gorenstein parameter distinguishes behavior of EB. So now everything graded, which is right here. A, so meaning I look here just at the graded modules, and well, maybe I should write this is a graded case. So this is defined to be graded modules. Modular and A. So just what are very perfect complexes. And so this distinguishes the behavior of this graded singularity category and how this relates to the category of A, which is just by definition category of graded A modules modulo the graded A modules concentrated in degree 0. So this is just the torsion part. So this is sometimes denoted by Huber of A. And so this gives you the effective variety given by A. And so, well,
what was the subcategory you quotient by in the
this one?
Yeah.
The additive, so just add A, so just like again the perfect graded complexes.
all shifts and thick A maybe.
Sorry?
I'd say thick if you want it to be a. Oh, sorry, the bounded derived category all add A. Yeah.
Yeah.
Okay.
Then oops. Okay, and so sometimes this thing here is over, this can also be identified with the category of coherent sheaves over X, where X, so where A is the ring of global sections of X. So the geometric context. I'm not actually defining what X is. There's a geometric interpretation of this, and I will draw J here. And so, well, how are these two categories related? So we have here this old graded A modules, and inside these graded A modules, so if you think about this as a graded ring, so we can just cut off at some degree. So a module here that starts in some degree, and we can just cut off a finite part here. And so this is denoted by dB mod equal A. We have this category sitting in here. And then, well, we can go to the proj, namely here is a functor A that is just a sheafification. And then we also have a functor back up here, which is the local homology. There are functors on here. And then on this side, there's the singularity category, so that's A. A. And so also one can find a functor B here, and then Orlov showed there's actually also a functor by M here. And so in total, what we get is that there exist actual functors between those two categories, namely back and forth. And so these are just, so phi is given as you compose, first you take local cohomology and then you go down with M. And psi is the other one, so first you go up here and then you sheafify. And so that's how these functors are given. And so the theorem is that the function psi is what belongs to phi. And then, well, the question is how are these related? So which of these categories is somehow the small one and which is the big one? And so that depends on the Borenstein parameter, namely one is always fully faithful, depending on Borenstein parameter A. And so, well, what can A be? So A is some integer. And so if A is greater than 0, so this is what's called Fano sometimes, or it's called Fano, then psi from the graded singularity category A onto dB proch A is faithful. And we somehow can see how this this category is generated. So you can actually find the same orthogonal decomposition. So of this category given following large A, and then well, if I write this as unit sheets over X, then I just take the structure sheet here. So I minus A 1 minus I. So I is where I cut. So if you cut at 0, it's just minus A plus 1 onto 0. And then here I still have the B I twiddle. So that means yeah, it's like this. So this is this functor, so I go BI when I truncate at I, and then sheepify of the whole. So here, this category is like bigger than the singularity category, and we can say exactly how much bigger it is. And so then this is the first case. The second one is now the nicest one, and that's also the one where the physicists are interested in. Namely, if A is 0, then the X is called Calabi-Yau. And in this case, we get an equivalence. So then phi from B A to energy category equivalence and yes, so that's the nicest case. And then third case, so that's the general type one. So if A is smaller than 0, then, well, the other factor is fully faithful for the phi, which goes from dB A very category. And yeah, we have again a semi-orthogonal decomposition of the singularity category. String A can be decomposed as A, and the shifts are minus I minus A. Plus 1, and then over the image. Okay, so this tells us in like integrated case nicely how the singularity category relates to the category of coherent sheaves or Proj A. And so just one example for this, so you can have a little feeling. So the easiest example is somehow if the A is sorry?
What is the K there?
The what?
The K.
Oh, the K is that K, the degree 0 part. So it's just the field. So if A is just polynomial ring in E plus 1 variables, and with the standard grading, so like the degree of each variable is 1, then Proj A is projective space over K of dimension D. Oops, I want to D, not D plus 1. We start at 0, so the D plus 1 variables, so I can really get projective space of dimension D. And well, what is the A invariant here? So there's actually, for commutative rings, you can easily calculate that. So A is always given as, yeah, the sum of the degrees of the generators. And if you had an ideal there, you add the degrees of the generators of the ideal. But so the degree here is we have D plus 1 variables. So the A invariant is D plus 1. So we are in nano case. And then, as I already said, somewhere, if you have a regular ring that's in singularity category, it's just 0. So we have the first thing of A is just 0. And so what is then the bounded derived category of coherent sheaves over Pn? Well, this is then just now only these line bundles. And so let's just start at 0. So we have O minus D. I should have minus D plus 1. No, minus D. Up to O0. And these are semi-orthogonal decomposition. And so this result is, I think, well known by Linson. And yeah, but in general, it's not that easy. And yeah, and I should also say that, of course, now this is all non-commutative. But if we bring that like in connection to our matrix factorization, so if we have a hypersurface ring, so if A is a hypersurface ring and commutative, I'll draw that in a different color here, ring is visible. So if A is S not F, and so now we are in a graded context, so we want that yeah, everything's graded. So F is a homogeneous polynomial in S, then from up here, we have already seen this category equivalent to the category of stable maximal Cohen-Macaulay modules here. And this is precisely the category upgraded matrix factorizations of F. And so this is actually something one can calculate. All right. So yeah, I wanted to make one more remark about Orlo's theorem. So you can also write this in terms of quotients. And this was done in a recent paper by Iyama and Yang. So Orlo theorem. Okay. Quotients. I'll put it here so that it's okay. So okay, I have 15 minutes left. Yeah, I wanted to do like some connection of all of this to cluster categories. And so, well, there is, I don't have time to say much more about this, about this maximal Cohen-Macaulay modules and how they're used in representation theory. But there is also a nice survey of Iyama, where he discusses maximal Cohen-Macaulay modules and connections to tilting and cluster tilting. So I'll just refer you to this. So MCMs in tilting, cluster tilting. ICM talk, which is called Tilting Cohen-Macaulay Representation. It contains a lot of references. And yeah, and applications. But I wanted to do one concrete application, more or less the same as Charlie, namely Grassmannian cluster categories, and how you can like somehow see Grassmannian cluster categories of infinite rank as matrix factorizations. Some of them. So this is last section, which is probably number 3 now. Concrete applications. Matrix factorizations, namely Grassmannian categories. Infinite rank, and this is actually joint work with Jenny August, Jim, Gratz, and Sibylla. Well, okay, so we have already seen the, so Charlie has already introduced the Jensen-King-Su category in the last talk, although a little bit differently than I kind of needed, namely the JKS. So if you remember, they Jensen-King and Su defined a category that categorifies the homogeneous coordinate ring of the Grassmannian, and it in particular has this cluster, the cluster structure on this homogeneous coordinate ring. And so Charlie denoted this by FKN, and actually in the paper of Jensen-King-Su, they also describe this as the maximum Cohen-Macaulay modules over a certain skew group ring, namely CXY modulo x to the k minus y to the n minus k. So this is just a commutative ring, curve singularity, and then you let un act on this, and so the un action is, so it acts on x via psi x and on y via psi inverse y, and so psi is the root of unity that generates the un here. And so in Jensen-King-Su, well, so this is an Ivanova-Gorenstein ring, so this category is particularly nice. It's homogeneous, and stable version is triangulated and also stably to Calabi-Yau. And this FKN is the qualification of coordinate ring of the Grassmannian of K space with K planes in N space. And so, yeah, the whole thing, so I just say the most important things that I need, namely that to rank 1 modules in here in FKN correspond to the simple coordinates. And also faster tilting objects. So there, if you have a maximal set of compatible Lucas, then this gives you a faster tilting object here, and if k equals 2, you also have the other direction, so equals to the maximal set of compatible Fluker coordinates of precisely the cluster tilting object. And so now, in this work, we were interested, oops, I should have written the infinity here. We're interested in, so we were interested in like what's happening if n goes to infinity. And so you can actually make sense of that geometrically. So what happens if n goes to infinity? So you can think of this as the Grassmannian and K points in a profinite dimensional vector space. So you are and K bar of us plus but what's happening to this category? So here's my category. So I'll just erase the theorem here. So if n goes to infinity, if you think topologically. So if you're like very close to 0, n goes to infinity, this y term is very small, so it disappears, and well, un becomes like all of integers, and so well, you're led to study, or so we propose that the correct definition of f a infinity should be or is the maximal Cohen-Macaulay module. So now instead of this group, one can show this actually becoming then a Z grading. Here is the right category to model the Rosmanian. So I'm not explaining that in very much detail, but you can look at our archive preprint where we explain why this category is precisely the right one. And so yes, so this is set graded, so meaning the degree of x is 1 and the degree of y is -1. And so somehow we should have this the cluster combinatorics encoded in this category of maximal Cohen-Macaulay modules. So in particular, we should be able to see that the rank 1 modules correspond to Fluker coordinates, and somehow cluster tilting correspond to maximal set coordinates. And in k equals 2, we should have a particularly nice picture. And so what is now about k equals 2? So actually, we have seen this ring already. So if k equals 2, if you remember, so then we're led to look at cxy not x squared. So commutative ring. Here we just have an x squared. Then this category has actually been studied in the context of matrix factorizations. So I mentioned that yesterday that it was proven by Buchwald, Broil, and Schreier that this is a ring of countable MCM type. And in particular, they nicely calculated all possible matrix factorizations over this ring. Because so this is like the corresponding geometric picture is the A infinity. And so we know actually, I want to do that on the big board, I think. So we know what the maximal Cohen-Macaulay modules are. And those projections. So from PGS, we know the first two columns, namely the matrix factorization and corresponding maximal Cohen-Macaulay modules. Maybe I will now it's okay. Word is done for me. Maybe I should say it's all right. I don't have to type on it. So R is cxy plus x squared, and S. Have to write so much. So matrix factorizations are classified as follows. So we have one matrix factorization that is of the form x parent 1. So this is, if you remember, this is the trivial matrix factorization. That goes from S as x parent 1, and that as a maximal Cohen-Macaulay module is seen as just a co-kernel of the map x squared, and that just gives us the R. Then we have another one named the XX. So yeah, x to x. And so, well, what's the co-kernel of x as an R module? Well, we mod out this ring R by x, so we are not, so we kill everything in x, and so we're just left with y. And then the countable part, so this is just 2 by 2 matrix factorization x minus x y to the I. And here we have the same matrix where I greater equal to 1. So there are infinitely many, but countably infinitely many. And what's the module? So the module of this matrix is then an ideal, it's also rank 1. And so it's the ideal generated by x comma y to the I in the ring R. And so now the combinatorial picture. So how does that relate to cluster combinatorics? So in type A, so you know, if we have finite n, then you can like picture all flickers as arcs on an n-gon. And so now what should happen now is like we should be able to picture our modules as arcs on an infinity gun. And so here, infinity gun, so that's like our contribution here. Yes. So this corresponds, so we have here the infinite point 0. And so now there is another point that I kind of wiped under the rug, namely the grading. So you have to like always consider everything graded. So maybe grading in here. So you can shift the modules. L is now just a shift, so L is Z. And so this R corresponds to the arc that goes from minus L to minus L plus 1. Then this here is the infinite arc that goes from minus L to infinity. And then these guys give us the finite arcs. These are the arcs that go from minus L plus 1 onto minus L plus I. So the arcs. So it's a nice picture, and actually now you can use the matrix factorizations to calculate that like the x behave as they should. So we get that x1 of 2 maximal Cohen-Macaulay modules Mn is 0, if and only if the arcs, corresponding arcs, are non-crossing. Okay, so, and we can also do triangulations. So we can determine what maximal rigid subcategories are, and also the cluster tilting subcategories. But, well, this is k equals 2, but actually you can look at higher k. And so if you look at higher k, then it's not of countable Cohen-Macaulay type anymore. It's like hopeless Cohen-Macaulay type. But also in this case, we could actually show that certain maximal Cohen-Macaulay modules of rank 1 correspond to Fluker coordinates. So, what about k greater or equal to 3? So, in this case, well, all maximal Cohen-Macaulay modules are far too much, but you can look at the subcategory MCM that's 0 of R. So R is now the xy from x to the k. And so this is the full subcategory of generically.
You're running out of time.
Yeah, I know. And so what you can show is, and I'll stop with that, that the rank 1 modules in MCM at 0 are, they actually correspond to the Fluker coordinates. So you can match them up with the Fluker coordinates. And then also you get the right x behavior, namely the x is 0 between 2 modules if and only if they are non-crossing. And yeah, I think that's everything I can say.
Very much for your nice lectures. Are there any questions? Yes.
Can I just clarify something? So in the k equals 2 case, if I remember right, in the statement about the x1s excludes the arcs going to infinity, right?
You say
And this-
louder.
In the statement about x.
Oh yes. Sorry. Yes, I was not detailed enough. Yes. So yeah, you have some. So if you have the arc, if you have the arc to infinity, you have some kind of one-sided x. Yeah, but for the finite arcs, it's precisely that. Yes.
But then, so on for higher k.
So for higher k, the thing is, so if you look at the subcategory, these are precisely that. So you're basically getting rid of the infinite arcs.
Okay, so if you take the 0 part for k equals 2, you throw out exactly these infinite arcs, and you're back to
Yeah.
the usual. Okay.
Yeah.
Okay, thanks.
I'm quite intrigued by a lot of your examples. The 2 matrices are equal. Is there something going on there? Is it just
That's a
special case?
good remark, actually, because so this just means that the corresponding maximal Cohen-Macaulay module is isomorphic to its syzygy. And yeah, I mean, this is often the case. So I mean, so usually we have this 2 periodic behavior. So you have that each maximal Cohen-Macaulay module is isomorphic to its second syzygy and fourth syzygy and so on. But it's very often that this happens. But yeah, I don't think I have a good explanation why this happens.
Thank you.
It does always happen for Kleinian singularities, right?
Yes. So always if you have a hybrid surface in even dimension, then it's always that the syzygy is isomorphic to the module because that on the right translation.
Yeah, it's one for
So and yeah, in the odd dimensions you can have like this splitting that happened. So if you remember the picture of the D5 that I drew, there was always this splitting, and that precisely means that the syzygy is split.
Yes, there's another question. Maybe.
I'm not sure I understood the question or answer from Matt. So I just want to understand. So that category here with the infinite arc, right?
Yes, so if you take all of the maximal Cohen-Macaulay modules, it includes the infinite arc.
Yeah, but say if I forget the infinite arc, right,
Yeah.
then I get the Holm-Jurgensen cluster category,
Yes,
right? So this is when I add the point at infinity, I'm sort of taking the homotopy co-limit closure of that category. So then this category without the infinite arc is 2 Calabi-Yau.
yes.
And then is there a similar way to interpret this full subcategory of?
Yes, we also show that this one here is 2 Calabi-Yau.
So this is also 2 Calabi-Yau.
Yeah. This is actually, I think, so we write this as generically free modules, but you can also write this as, Yoshino calls this the locally free on the punctured spectrum. And I think it was already shown by Auslander that this is 2 Calabi-Yau.
If there are no more questions, let's thank Eleonore for her series again. Okay, so we have a longer break and we do until 10 past because we have tea now.
Yeah.